Welcome to this new lesson of heat transfer. Last time we were talking about the heat conduction equation, and at the end we wrote it down in the case of one-dimensional geometry. So in this case we have, for example, a thin wall, so we can study the problem in Cartesian coordinates, and one side of the wall is at position x. The other side of the wall is x plus delta x. So we define in this way our control volume, and heat enters the control volume from the left, this is Qx, and leaves the control volume on the right, and that's Qx plus delta x. So if we use the first law of thermodynamics, so we write an energy balance for this control volume, Qx minus Qx plus delta x plus some heat generation that may occur inside the control volume, it's equal to the change of thermal energy over time. Then we looked at a little bit more at the form of delta E, the change of thermal energy, and also we looked at the heat generation. So these two terms can be written in this way. Delta E is the mass times Cp times the change of temperature in that interval of time, dt, delta T. And if we write the mass as the density times the volume, which is A times delta X, this is the form of the change of thermal energy. And the heat generation in the control volume is the heat generation per unit volume times the volume, so A times delta X. So then what we have to do now is take these two quantities and substitute them in the heat conduction equation, and then we divide by the volume. So we obtain this equation. So this term here is due to the heat conduction, then we have heat generation, and this term on the right is the change of internal energy or thermal energy inside the control volume. We can now take the limit for delta x and delta t going to 0, so we get a differential equation. We can also eliminate Q from this equation by using Fourier's law. So the unknown in the equation will be the temperature. So we find a differential equation that has this form. So partial x of k of partial t partial x plus heat generation, it's equal to rho Cp partial t, where big T is the temperature and small t is time. So this equation is valid in one-dimensional case. In the unsteady case, k can vary in space in general, and we also have heat generation. If we now simplify this case even further, we can take, for example, the case of constant thermal conductivity K. So this quantity can now be taken out of the first partial derivative over space x, and the equation reduces to this form. So now we have the second derivative of the temperature with respect of x. Now, if we simplify even further and we consider a steady case, then partial t partial time is equal to 0. We have no heat generation. We find simply that the second derivative of the temperature with respect of x is equal to 0, and this is the simplest form of heat conduction equation. So this case was for a Cartesian case, so Cartesian geometry, but what instead if we have a long cylinder, we can do exactly the same analysis and we find a similar equation, but now we observe we cannot simplify the area, because the area, the surface area of a long cylinder, is 2 pi r times L. Well, L is the length of the cylinder and R is the radius. We cannot simplify A because A depends on R, and R is inside the partial derivative with respect to R. Therefore, we can only simplify 2 pi L. So this is the equation in cylindrical coordinates for heat generation one-dimensional unsteady. And we have the K that in general can depend on the radius. We can do exactly the same exercise for a sphere, where the area will depend on the radius squared. So all three cases, one-dimensional, can be written in this compact form, where we have introduced an exponent n. So if n is equal to 0, we have the Cartesian case. If n is equal to 1, we have a cylindrical case. And if n is equal to 2, we have a spherical case. This is for one dimension. Obviously, we can extend our analysis to 3 dimensions. And so the conduction equation for K equal constant in 3D assumes this form, where we have introduced the Laplacian of the temperature. And of course, the Laplacian can take different forms if we have a Cartesian, cylindrical, or spherical case. In the case of Cartesian geometry, the Laplacian of the temperature takes this form, so it's a scalar, is the sum of the second derivatives with respect of x, y, and z. So now we have found our differential equations, but to solve our problem, we need boundary and initial conditions, because we want to find the temperature as a function of space and time. So we need to solve these differential equations, and to do so we need boundary conditions in space and we need an initial condition in time. Let's look at the simplest case of heat conduction. We wrote it down before. That's the case of steady, one-dimensional, no heat generation and constant thermal conductivity. So we have the second derivative here, I should say, equal to 0. In this case, if the second derivative of the temperature is equal to 0, then the temperature is linearly related to x. So we have T equals C1 times x plus C2. And C1 and C2 are unknown constants. To find them, we need boundary conditions. So we have here a second order differential equation, ordinary differential equation in space. This means that we obtain 2 unknowns when we integrate this. So 2 unknowns means that we need 2 boundary conditions in space. What about in time? So if we have an unsteady problem, for example this one, now we have the partial derivative of the temperature with respect of time. We still need 2 boundary conditions in space because we have a second derivative of temperature with respect of x, but we need only 1 initial condition in time because we have first derivative of the temperature with respect of time. We just need to specify the temperature every point in space at time equals 0, for example. So we know the temperature at the beginning. Okay, let's look now on specific case for the boundary conditions. What's the simplest boundary condition we can specify for our problem, heat conduction problem? Well, we can specify the temperature. For example, we can say that x equals 0, at x equals 0, the temperature at any time is equal to T1, a known temperature. Or we can say x equal L, certain location in space, the temperature TL is equal to T2. So we know the temperature at these two fixed points. Another case, instead of specifying the temperature, we could specify the heat flux. So Q dot, remember when we have a small case Q, we have a heat flux. So the units are watts divided by meter squared. So in this case, we have Q dot, that's known, equal to minus K partial T partial X at a certain location X equals 0, for example. So we know the temperature gradient at that point because K is known. It's important to note that in this case, we don't know the temperature at that location, but it doesn't matter. We can still solve the problem and find the temperature at that point X equals 0 afterwards, once the solution has been found. A subcase of the previous one of specified heat flux is when we have an insulated boundary. In this case, K partial T partial X, it's equal to 0. So there's no heat flux. This is called adiabatic case. It's right here. Adiabatic case. So there is no heat flux through that surface. The surface that's perpendicular to the coordinate X. So the temperature gradient is 0. We can have another case where we have instead a thermal symmetry. In the case of thermal symmetry, for example, here we have a wall and maybe we have some heat generation inside. The temperature at the two sides of the wall are kept at equal value. So this line here that I've drawn in blue is a line of symmetry for the thermal problem. We have partial T partial X and X equal L divided by 2, which is the midplane. It's equal to 0. Or in the case of a sphere, for example, we could have partial T partial R at R equals 0 equal to 0. So this is the center of the sphere, which is also a symmetry point. And of course, this thermal boundary condition here has strong analogy with the insulated boundary. A more complicated case, which is probably my favorite case, I can say, is the case of a conduction-convection boundary conditions. For example, we can have a wall, here colored in blue. So this solid wall, there's some heat conduction flowing here, and this conduction must be equal to the convection outside, because this solid wall is exposed to some convection, some air, for example, in motion, and that's characterized by a certain heat transfer coefficient H, and the temperature far away from the wall is T infinity. So if you remember, we studied the surface energy balance. So if we consider an energy balance at the surface, then the Q conduction must be equal to Q convection. So all we have to do is use the Fourier's law of conduction for the heat transfer in the solid wall, and we can use Newton's law of cooling for the convection in the air. So these two are equal. So now we have a relationship between the gradient of the temperature and the temperature at that point. This is a sort of, it's a clear example of Robin boundary condition, also called mixed boundary condition, where we don't know the gradient, we don't know T, but we know a relationship between them. And the last case we study today is the case of interface boundary condition. Let's say that we have now two walls, two flat walls. They are completely touching each other, so there are no gaps in between. And the wall A and wall B have two different thermal conductivity, so Ka and Kb, and we want to find the temperature distribution Ta of the wall A and Tb of the wall B. What are the boundary conditions at the interface? Well, if the two walls touch each other, then they must have the same temperature at that point. And the other boundary condition and the heat flux are the same. Because, again, for conservation of energy. So the heat conduction that leaves wall A will enter wall B. So we note here, since we consider the case where Ka is different from Kb, then the gradient at this point will be in general different, whereas the temperature will be the same. So thank you very much for listening, and I'll see you in the next lesson. Bye!